gratings. And so before we actually get into what a diffraction grating is, let's go back to the double slit. In the double slit, there were bright and dim. There's a bright and dim alternating diffraction pattern. Now, when I say diffraction pattern, it's because it arises due to diffraction, right? And diffraction comes from Quickens Principle, remember. So what happens if we add more slits? Instead of 2 slits, what if we have 3 or 4 or 5? So for the sake of ease of the arguments I'm about to make, let's look at 4 slits. So the picture that I'm going to draw is, I'm going to do my best to make it as good as I can. But let's imagine that we have four. Let's imagine that we have 4 slits, all equally spaced. So this distance is d, this distance is d, all of those distances are d. And again, we just shine a coherent light source that's in phase with itself, through all 4 of these slits, and then these 4 slits will each act as point sources. Now, let's look at just some arbitrary points, say a double A. So each of these slits will have a path, or each of these sources will have a path to that point. Oh, this is so hard to draw, right? One more time. Again, this is an approximation that's very blown up because remember that D is supposed to be much smaller than L, and so all of these angles should be the same, or at least very close to the same. So what we have is we can draw a perpendicular to each of these lines, connecting them up, like so, and that'll let us calculate the path difference path length difference between the slits, or the path that each slit takes to get to the same point. And so again, these are all right angles. They all have the same angle theta. Sorry that this is very tiny. They all have the same angle theta. And so that means that each side length, all of those side lengths have length d sine theta, right? That has to be true, that's just trig. And if they all have the same angle, then they all have the same side length. 100%. Oh boy, 100%, there we go. So they all have the same side length. And so, I just want to make a note here for the record, so for your guys' notes. Note that, very blown up, D has to be much less than L, and theta has to be much less than 1. So we're looking at small angles and small slits relative to the distance. So remember that this distance we call L, and then that angle theta is also the same as this angle theta, and they all make the same angle with the horizontal. So the first question that we should ask when we are looking at more than 2 slits is, what do we mean by bright spot? Or a bright fringe? So the reason we ask that is when we just had 2 slits, it was obvious. A bright spot was when the 2 things constructively interfered, and the dark spot was when they destructively interfered. But now we have 4. So you have the possibility of some of them constructively interfering, some of them destructively interfering, some of them partially interfering, or whatnot. So we need to make sure that before we characterize where the bright spots are, we need to actually understand, or we need to define what a bright spot is. So what we choose to do, what the convention is we require all 4 paths contribute constructively. So we require that they all constructively interfere with each other. So theta being much less than 1 means it's a small angle. And the reason we have to do that is because otherwise what happens, or what will be required later, is no longer true, right? Because we use this approximation that sine of theta is equal to tangent of theta a lot, and that's only true. That's only true when the angle's theta. Sorry, when the angle's small. That's why we require that theta is much less than 1. In general, it doesn't have to be the case, but it does make these calculations harder. But again, theta, like 90 degrees, is when theta is like 1.5. So like, 5 degrees, which is, like visibly deviated, is a relatively small angle. So why do we require that all 4 paths contribute constructively in order to count that as a bright spot? Well, first note that even if just 2 paths caused constructive interference and the rest were just kind of like partial, whatever, like half constructive, half destructive, or something like that, then it wouldn't be as bright as it could be if there were all 4. So the brightest spots that we would physically see are going to be the spots that have all 4 constructively interfering. So what does that mean? It means that we require each length difference to be equal to lambda. Remember that in order to get constructive interference for the 2 slits, you had to have that one of the path length differences is, or that the path length difference between the 2 slits is either lambda or 2 lambda or 3 lambda or whatever. So in this case, in order to get constructive interference between all 4, we have to have that the path difference between any 2 paths is a multiple of lambda. Or put another way, the path difference between 2 adjacent paths, like these 2, for example, has to be equal to lambda, because then the path difference between, say, the first and third path would be 2 lambda, the first and fourth path would be 3 lambda, the second and fourth path would be 2 lambda, and so on. And so they would all constructively interfere. You could have equally said that we want the path length difference to be 2 lambda, that would also work, but this is the simplest case. So what does that mean? That implies that d sine theta has to be equal to, and lambda has to be a multiple of lambda, where again n is an integer, so negative. So -2, -1, 0, 1, 2, right? So this is actually the same formula that you would expect for a double slit. So does it produce identical results? Well, no. So we have to be careful here. While the bright spots, or the bright fringes, are at the same place, as in the double slit, the dark spots are not. And perhaps that's not so surprising, right? If we have 4 sources all contributing constructively at one location, then in order to have energy conservation, you would expect that you'd have 3 dim spots, so that the total energy, the total power, is the same as if it were equally spread out. So how do we get dark fringes? Well, in order to have a dark fringe, we need to have destructive interference between all 4. Now, what we could have is we could have that they all like combine in some right. The point I was making, and I'll actually make this point more clearly later, but the point I was making is just that the reason why we had equally many dark spots as bright spots in the double slit is because if you took all of the energy in a bright spot and smeared it out over the dark spots too, then it would be the same brightness as if it were just one spot, like just no slits at all, is just the source as it normally is. And so here we have 4 sources coming together to one bright spot, so you have to have 3 dark spots to smear it over. That was the point I was making. Right, so dark fringes. So we could have some complicated arrangements, but they all constructively interfere together. But we can break this down into, because we have 4 slits, into a simpler case. If we just require that each slit destructively interferes with one other slit, then that would be sufficient, right? Because that would mean that, let's say, slit 1 and 2 destructively interfere, and slit 3 and 4 destructively interfere. Well, that would mean that 1 and 2 together produce no light, and 3 and 4 together produce no light. So there's no way that you're going to get light out of that by combining 1 and 2 plus 3 and 4. So all we need to do is just pair them up so that they destructively interfere. And that's exactly what we do. And it's actually relatively easy to show how that can happen. So let's look at the different cases that we get. So let's suppose that d sine theta was equal to 3 lambda over 4 instead of lambda, right? That would mean, and I'll leave this to you guys to think about, that slit 1 and 3 have a path length difference of 3 lambda over 2, and slit 2 and 4 have a path difference of 3 lambda over 2. And so because we know that destructive interference occurs when you have a path length difference between two sources of some odd multiple of the wavelength divided by 2, or some like half wavelength multiple, like lambda over 2, 3 lambda over 2, 5 lambda over 2. This means that we would have destructive interference. So at the angle where d sine theta is equal to 3 lambda over 4, we would get destructive interference. There's another case. Let's say d sine theta is equal to lambda over 2. Then, slit 1 and 2 and 3 and 4 have path differences of lambda over 2, right? So let's go back into the picture. If that little line there has length lambda over 2, then that means that the bottom 2 will destructively interfere, and the top 2 will destructively interfere. And so again, we'll get total destructive interference. There's one more case. When d sine theta is equal to lambda over 4, we can analyze this again. So slit 1 and 3 have path length of a path difference of lambda over 2, and slit 2 and 4 have a path difference of lambda over 2. Does this apply when we have more slits, or no? So this sort of argument will work for more slits. It's just the easiest to observe for just 4, because basically you're just looking for I'll leave it at that. But yes, it does generalize. So what does this mean? That means, so there is one bright spot. So what am I trying to say? Let's look at the angles that lie between d sine theta equaling 0 and d sine theta equaling lambda. So between sine theta 0 and d sine theta equals lambda, d sine theta equals lambda is the first bright spot, by the way, right, from this formula. So between the central bright spot, which occurs here, how many angles would correspond to dark spots? Well, if we could solve for theta in all of these cases, and we would get a range of thetas, and we would find that all 3 of these situations, where d sine theta is 3 lambda over 4, lambda over 2, and lambda over 4, those all produce thetas that are between the 2 thetas that correspond to the central and first bright spots. So this would mean that we have 3 dark spots between the central maximum and I'm going to use a new terminology here, the first order fringe. First order fringe just meaning the first bright spot. And the reason for that is because the path length differences are between 0 and lambda. It's 3 lambda over 4, lambda over 2, and lambda over 4. So we can generalize this. So generalizing this to m slits. Actually, let's use m slits. M is just an integer. So m could be 100 or it could be 8. The bright spots occur, well, the bright spots were no different for 4 slits, so it's reasonable to conclude that it's no different for any number of slits. And indeed, that's true. The bright spots still follow the formula d sine theta equals n lambda. Still true, where d is the distance between the spots. Yes, that's precisely what it means, gentlemen. Now, further, what this means is that we get m minus 1 dark spots between the bright spots. So the more slits you have, that means that you get more bright spots more dark spots between bright spots. But we expect that the bright spots and the dark spots are the same size. So what's the conclusion here? The conclusion, and what we eventually see, is that you get narrower and narrower bright spots, and they're more and more, they're less spread out. They're more and more point-like. So you just get a narrow peak in the middle, and then another narrow peak some distance away, and then you have dark everywhere in between. So now we can actually talk about diffraction gratings. So a diffraction grating is an object. It's basically just a setup that has many slits. That's all it is. It's just a thing that has a whole bunch of slits, like orders of hundreds or thousands. In particular, the amount of slits is specified by the line density, which is just equal, typically, to the number of slits per millimeter. So you say something like, oh, well, maybe this diffraction grating has 1,000 slits per millimeter or something. And that's a fairly standard type of measurement. And so there's really a lot of slits, which means that your bright spots are going to be very, very narrow, and there's going to be basically emptiness between them. Come on. Okay. So, but we characterize our multi-slit setups using the distance between slits, right? Not the number of slits per distance. So, formula, we just take the inverse. Because, for example, if the line density was 2 slits per millimeter, you just take the inverse, and the distance between slits would be 0.5 millimeter, right? You take the inverse of the line density. So what we can do is we can try to answer, or we can do a quick demo, and I'll do one for you. I'm not sure how well it's going to turn out. So what happens when we shine white light? Remember, white light is not on the electromagnetic spectrum. It's just a combination of all of the wavelengths through a diffraction grating. Now, I would like to show you what happens. Unfortunately, I don't have an actual diffraction grating. What I have is a piece of a CD that I cut up. Now, a CD almost works like a diffraction grating. In particular, there's a reflective bit that's silver. That's what you guys are seeing. But then the plastic itself has little tiny divots in it, and those little divots will act as slits. And so what I'm going to do is I'm actually going to reflect white light off of this surface, and we'll see what the reflection looks like. So let's project onto the wall, turn off the light, do as best I can, and let me go get a flashlight really quick. I could use my phone, but that's an LED light. Oh, this is an LED light too. Whatever, this will do. So I'm going to do my best to make this look good, but I make some problems here. So this flashlight, standard flashlight, CD. So Okay. Let me move out of the way. Or move this chair. That'll do. Okay. See that rainbow? So basically what's happening here is there's a reflection occurring, and we're going to get into how reflections work later. But the central bright spot, that's the central bright spot is the part that just looks like a normal reflection, right? And then you see like normal lighting scenarios, it's a little bit more complicated than that, the reflection here. And then you just see randomly a rainbow. Now, the question is why do we see a rainbow? Right, so there's the bright spot, and you'll notice that if I angled this a different way, if I put this head on, see if I can get this to work properly. Maybe if I use yeah, so let me pull you away. A little bit further away. See if I can zoom out a little bit. No, unfortunately, you can't see both sides. So what you're seeing, or at least what I would, oh, you know what? Let me try my phone. My phone has a smaller LED in it. That works. No. Okay. So we'll have to deal with what we saw. There's a better demo coming up in a minute. So notice that there's the central bit that the flashlight itself is blocking. But then notice that there's a rainbow bit higher up. And it looks distorted because it's reflecting off of a complicated surface. But it is rainbow-y. At least that's the hope. And you can see that it is in the correct order if I do it at an angle. You know, it goes from violet to red. And the cis shape and the curvature, that's an artifact of the fact that I'm reflecting it off. Now, that's all great, but why does that happen? So we can explain this a little bit at least. Let me put this back here. I can explain why this happens at least to some extent. Well, I mean, I can explain why it happens, period. So what you would have observed with a proper diffraction grating is that you have a bright white reflection in the middle. And that is the central maximum. And then we saw, then we saw a spectrum. Starting with violet, that was the part closest to the bright white spot, and going to red. This was the rainbow that we saw. Why does this happen? Well, right occurs at a particular location. It occurs at a particular angle, right? It occurs when d sine theta is equal to lambda. That is the first right fringe. So for a fixed d, there we go. It's the same for all of the light. And smaller wavelength, we would get that theta is smaller, which implies that we would get violet first. And I can explain that again in words. So you fix d, and so we look at how theta changes, i.e. the position of, remember that theta tells you the angle away from the central maximum that the first bright spot is. So if you make theta smaller, what happens to, sorry, if you make lambda smaller, what happens to theta? Well, at least for small values of theta, sine theta is approximately theta. So for small values of theta, so if we're looking at small angles, and this is true up to pi over 2 anyway, if you increase theta, you increase sine of theta. So that means if we decrease lambda, we would have to be decreasing theta. And so that means that the first bright spot occurs for smaller wavelengths closer to the central maximum, because those are places with smaller angles. Which is why we should have observed that we have a violet bright spot first, because violet has a wavelength of around 400 nanometers or so, whereas red has a wavelength of 700 nanometers. And so the angle where the bright spots occur for the different parts of the light are different, i.e. you have a bright spot for violet that occurs close to the maximum, and a bright spot for red that occurs further from the maximum, and all of the colors in between lie along a spectrum. So what a diffraction grating is actually doing is it's basically splitting up the light. But just as a note, there is no splitting at the central maximum, at the central spot, because at the central spot, it's just d sine theta equals 0. It doesn't depend on the wavelength. And so you just get that theta equals 0 for that first bright maximum. Now, just as a quick aside, I want to show you something else. So we saw that using just a white flashlight, we saw a rainbow. And the question is, can you always split light? I.e., is it possible that I could take the spectrum that I just showed you and keep splitting it and making it wider and wider forever using diffraction gratings? I.e., is light infinitely divisible? And so, in a sense, yes, but that doesn't mean that all a diffraction grating is doing is just spreading out the light. It doesn't mean it's just smearing it, because I want to show a quick demo. So here, small laser pointer, very special laser pointer actually. I had it made for me custom because it's a very special wavelength. It has a wavelength of 513 nanometers or so. It's like a limeish green, maybe just a pure green. And so what I'm going to show you is I'm going to show you what happens when we have just a single wavelength. I have enough room for this. Yeah, so that would happen with a finer diffraction grating where d is smaller. Where d is smaller, where the spacing between slits is larger, but I only have a CD, so it's as good as it gets. So I'm just going to take this single wavelength, 513 nanometers, and show you what happens. So here, there's a central bright spot. I'm going to try to line it up with the camera. So let's see if I can get this right. I need to move the camera further away. Or actually, I can move this closer. So notice, hopefully you can see. Let me actually turn this sideways, maybe it'll be more visible then. Notice that there's two spots. So the spot on the right, let me move this back into the frame. The spot on the right, I think it's on your left. The spot that's brighter anyway and doesn't just look like a line, that's the central bright spot. The spot that's darker is the first fringe. And so what you're seeing is it's not spreading it out. It's literally just a line there. And so the reason that happens is because this is a single wavelength. It just produces just a single color, whereas white light isn't. Now let's look at a different example. This is something that I wanted to show you guys, and I had to run to campus yesterday to do. Here is another laser that I own, the big boy from 1995, I think. It's an argon laser. It might blow the fuse in my house, so if I disconnect, that's probably why. Well, wait a minute, no, I'm on a tablet, so that should be fine. Oh, well, if I blow the fuse, then the Wi-Fi will go out, so yeah, I'll disconnect. But it's because this thing sucks up a ton of power. So I'm going to turn it on. It's noisy. I'm a big fan of this power supply over here. Really noisy. Sorry. We put back. There's like a knob and switches and stuff. This was used in the DNA sequencing machine actually in the 90s. I got it aftermarket. So I'm going to turn the key, turn it on. It has a quick startup time. Or a slow startup time rather, because safety, it's supposed to there's supposed to be a delay between turning the key and turning it on because it could damage your eyes or something. So what I'm going to show you is something else interesting. So far we've seen a white light turns into a spectrum when it goes through diffraction grating. a single wavelength splits or doesn't do anything. So is white light something different from a single wavelength? Is it something else entirely? Well, not quite. So first, let me hold up this paper so you can see the backsplash. First, this is what this beam looks like. It's a nice aqua blue. It looks better in person, in my opinion. But I'm going to turn this around, or rather, I'm going to, I should probably put on goggles. There. I hope this works. I just don't want to reflect it into my eyes. Let's bring this back further. Oh boy. Oh, I lost my power cable to my tablet. There we go. Power cable back in. All right, so let's see if I can get this to work. All right, so the power. Come on. I've gotten this to work in lecture before, in person. All right, so I'm going to direct the camera where the spots are instead of showing you a fixed image and trying to aim it. It's kind of hard to do. So there, on my ceiling, is the bright spot. And you'll notice that it's basically the same color. Let me find the diffraction bit. And there, I don't know if you can see it, there is a whole bunch of different wavelengths splitting. So what we see is we see a bunch of distinct spots. Now, why do we see that? We can answer that question now. What this means is that the source of the light, in that case, this laser, produces, well, if you count them, maybe 5 distinct wavelengths that are all different. And so what we're seeing is we see that white light is just a spreading out. It produces all the different wavelengths, whereas a laser, standard laser, produces maybe just one, like we saw with the green one. And this laser produces maybe 5. And you can actually see that there's green on the left, violet on the right. The violet is really dim. And if you were able to look around in my house, maybe I can just angle this up, there is the bright spot. Where does the diffraction pattern go? And so we see again that the violet is closer to the bright spot, which isn't surprising because we know why that happens now. So this is a thing. This is a thing that happens, and now we can understand why this happens for this particular laser. So the reason why this happens, I'm gonna take off my fashionable laser goggles. The reason why this happens is because we can now understand why we say that light is a spectrum. The visible wavelengths that we can see occur between 400 to 700 nanometers, and if you were to combine all of those wavelengths, you produce white. The way you make white light is just take light that's from every frequency or every wavelength between 400 and 700 nanometers. This laser produces wavelengths that range between about 450 and 515, and it produces, depending on how much power I give it, if I were to turn it up to full power, blow the fuse in my house. But this laser produces somewhere between 5 and 9 wavelengths. If I turn up to full power, it produces 9, but it's just not exciting all of those wavelengths. Yeah, so in this case, some of the first order fringes were brighter, and that's just because, the way this laser produces light, it favors some wavelengths over others, and so this one has some dominant wavelengths. I think the dominant one's at 478 nanometers. Is that like that bright blue one? And that's why this color that you see from this laser was like a cyan, or like a bright blue or a sky blue, which isn't quite on the spectrum. It's a combination of light greens and violets and blues. And this is probably my favorite laser. Unfortunately, it's very hard to turn on and very hard to point at things, but it's a very nice laser because it produces a few different wavelengths, which is good for demos. So that's enough with this thing. Let's continue on. How do we describe the intensity for diffraction grating? Well, it's not complicated than a double slit because you have a whole bunch of different sines and cosines adding up, or sorry, a whole bunch of different sines with different arguments adding up. There's a lot of trig involved. But in principle, it's similar to the double slit. In fact, the double slit is just a special case of the multi-slit or the diffraction grating. It's just the simplest case. For n slits, each bright spot is n squared greater, or is n squared more intense, let's say, from a single slit. So we can think about this way. So there's, first of all, we know that there's going to be n sources of light coming together. So the amplitude of the light at the bright spots is going to be n times higher, right? And we know that the intensity goes as n squared. Or sorry, the intensity goes as amplitude squared. So already it's n squared more intense than the light from just a single one of these slits. Another way to view it is that there are n slits, so you add up the intensity from n of those slits, and the light is less concentrated between the slits, i.e. because the light is narrower by a factor of n than if you had just had one slit, because you have more dark spots between. So those two factors, the n slits and it's n times narrower, also could be used to derive that the intensity is n squared. I prefer the first argument though. You have n times the amplitude, so you have n squared times the intensity. So I've shown you this thing, but now we can actually talk about why we care. So it turns out there's this method of determining what stuff is called spectroscopy. And spectroscopy is going to be the answer to the question, what are diffraction gratings good for? So you may or may not know this, but atoms and molecules only emit light at particular frequencies. So if you've taken like inorganic chemistry or maybe some physics classes before, like in high school or something, you might know this. And it turns out that frequencies that a substance emits, that's how I want to phrase this, characterize that substance. So what I mean by that is I mean that if you know the set of frequencies that a substance can emit, like, and there would be a lot of them for any complex substance, even something as complicated as water has a large emission spectrum. If you know those frequencies that substance emits, then you can basically, with very high degree of accuracy, determine what that substance is made out of. I.e., you have some material, some unknown material. Well, figure out what substances it emits or what frequencies it emits. Go look at your table, and you find, oh, it's made out of titanium dioxide or something. And it's just there's like a one-to-one relationship there. So if we can determine, then we can determine the substance, which is obviously very useful. Why might this be useful? Well, what if you're going mining, for example, and you want to see if the ore that you've sampled contains gold? Well, how do you do that? Well, you could destroy your sample, melt it down and see if you get a little tiny gold bead at the bottom, or you could just effectively shine light at it. And if it emits the appropriate, if it reflects and emits the appropriate wavelengths, then you'll see, oh, well, this is gold, this is some gold ore, or something like that, and then you would just know what it's made out of. So another reason, a reason that's, oh, drop my notes, a reason that's slightly closer to my heart, why we might care about this is, what if you can't just get to this stuff, right? In general, nobody's been to the sun. Like, we know what the sun looks like, but you can't just go there and test it. So how do you figure out what the sun's made out of? Well, you could use spectroscopy to do so. Just measure the light that it emits, and that'll tell you what it's made out of. In fact, the closest thing that we can send, that we have sent to the sun, is the Parker Solar Probe. And it has, like, you know, it'll only last a few years because it'll fry eventually, but getting close to the sun is actually harder than getting away from the sun in general. Anyway, so another feature that, or another reason why we might care about the about spectroscopy is for the following reason. So first, I want you guys to recall the Doppler effect for light. The Doppler effect scales frequencies by the following amount. Frequencies. For light, it's C plus or minus V divided by C minus plus V, right? That was the factor, and we covered that, I think, in the second lecture. So the thing to note here is that which is useful. That means that a given substance has a fingerprint. By the way, the reason I'm bringing up, oh, audio is weird. Is it because it's far? If I put the camera here, is it better? I can also let me select, oh, that's why. Okay, is this better? Better, worse? Okay, yeah, it's because it was using my built-in, the built-in microphone and not the camera's microphone. Sorry about that. Right, so the reason why I'm bringing up the Doppler effect is that in general, in the universe, things are moving, right? And so how is it that, like, if something's moving very, very quickly, how is it that we can figure out what it's made out of if there's like two effects that are competing? Like, one is the frequencies that the light emits. If it wasn't moving, we could just look at the light it emits and see, oh, well, it's made out of this, this, and that. But if it's moving, how can we tell? Because the Doppler effect will change the frequencies. The point that I'm about to make is that a given substance has a fingerprint described by the frequencies and their relative spacings. And that's the important part, because the Doppler effect changes every frequency equally, or scales each frequency equally, what we can do is we can determine the ratio between emission lines, is what they're called, the distance or the frequency gap between emission lines, that will always stay the same. So, let me show you an example. A quick image. So I'm going to do a new share really quick, just to this other tab. So this is an example of, I want to say the sun, but it doesn't really matter. The point is it emits light at most frequencies except at a few dark spots. That's at the top. If that thing is then moving towards us, or if it's moving, all of those frequencies will be Doppler shifted. But the important part is that the relative spacings between them stays the same. So notice that the actual gap between, say, the yellow line and the red line changes, right? It gets wider here, which would mean that it's moving away from us. But if you divided the distance between the red and the yellow and red gap by the distance between the green and yellow gap, and then did the same in the bottom, you'd get the same number out. And I can show you more explicitly with another example that I'll draw. So just as a quick note, just to summarize what I said, the ratio of distances is fixed. And that should be easily provable by you guys. Just take say 3 frequencies, F1, F2, and F3, scale them all by the same amount, and then take the ratio of the differences, and you'll find that it's the same. So let's say that, here's just a quick example. If the frequencies were unshifted, maybe our spectrum, which is what's usually called, would look something like this. So maybe this distance is 10 units. So you have so my point is you'd have a bright spot at this frequency, a bright spot at this frequency, and a bright spot here, or maybe a dark spot, because that's how most things work. And then you have a distance here of 5 units. And those units are just whatever units you want to measure them in. So the ratio is 2 to 1. If those were shifted, well, you'd multiply all of these wavelengths by the same number. So you would get something like this. And then this distance, maybe this distance is now 8 units, but then this distance would be 4 units. And so what happens is that the ratio is the same. So the way that we characterize a substance is not, at least in astronomy and astrophysics, is not the wavelengths it emits, like you may have thought. Rather, it is the ratio of the wavelengths it's the ratio of the emission lines, the ratio of the distance between emission lines, because that doesn't depend on how the thing is moving. And so that's how we can figure out a star or a galaxy that's 1 billion light years away and is moving very quickly relative to us. That's how we can figure out what it's made out of. And that's how we know that most of the universe is made out of the same stuff. So if we were to observe these two spectra, say it in different parts of the universe, we would say these are the same element or the same stuff. They're made of the same things. So what this does is this helps us determine, it helps astronomers determine how fast objects are moving towards or away from us, because we know what the stationary spectrum is for everything. You can just make it in a lab and measure it. And so if you can determine what the stuff is made out of by looking at the ratios, and then you can figure out what the actual values of the frequencies are, you can compare the shifted frequencies to what we know the frequencies should be. And then from there, you can do some math using this Doppler shift formula, and we can figure out how fast something is moving. And as we saw from the first homework, if you know how fast something is moving, you know how far away it is. So this is just one way to figure out how far away something is, which is amazing. You don't need to know a whole lot about a thing. Like you just need to be able to measure its light, and that will tell you, approximately anyway, how far away it is from us just by using Hubble's law and this Doppler effect. It also helps us identify unknown substances, by the way. Like on Mars, on the Mars rover, there's a little laser that shoots at the ground and vaporizes stuff, and it causes light to be emitted. And then the rover measures the emitted light and does spectroscopy on it to try to determine what it's made out of. So this whole thing of diffraction gratings, which is basically splitting up light into its components in order to figure out what the component wavelengths are, is remarkably useful. And you can use prisms for this too, but diffraction gratings tend to be a lot more effective because they cause more splitting. All right, so that's all I have to say on diffraction gratings. We're going to move on to a different subject now. We're going to talk about something that you may have not thought to happen. We're going to talk about single slit interference. So you may have thought that a single slit wouldn't have interference because it's just like, what is it interfering with? It's just itself, right? So in the discussion that we've had before, I'm going to move this back. In the discussion regarding multi-slit setups, we assumed that the multiple slits were point sources, i.e. each slit produced or acted precisely as a point source. But in practice, this isn't possible, because in order to behave like a point source, the width of the slit has to be infinitesimally thin. And that would mean that it just doesn't let any light through it at all, right? And so if you want to have any light come through a slit, period, you have to have some sort of width, meaning that it wouldn't behave like a point source because it's not infinitesimally thin. So in order to understand this, let's first look at a simpler case. What if the slits are wide enough to let light through? And when I say wide enough, I just mean some physical width rather than infinitesimal. So we're going to do this, to answer this question, we're going to consider just a single, I'm going to put in quotes, wide opening. So rather than considering infinitesimally thin, but a whole bunch of slits, we're just looking at a single slit with just like some fixed width. So the picture here is you have on the left-hand side your source. Maybe it has width A. And then on the right, you have some, you have a screen. And so the question is what happens? Well, there's going to be light that comes through. And so if we look at a particular place, light is going to come from all of the different places in the source or in the slit, right? So unsurprisingly, there's a bright spot in the middle. This seems obvious, but the point I'm about to make is not obvious, that there are other bright spots too. So why is there a bright spot in the middle? Well, it's not just because all of the light goes there, because it doesn't. The light goes every which way. Rather, if we describe each infinitesimal point as being paired with another point on the opposite side, then each of those points are traveling the same distance to get to the center. So they would constructively interfere. So we call those Huygens points. All Huygens points pair with another on the opposite side. So remember, Huygens principle, let's zoom in on this a little bit, would say that every single infinitesimal point behaves like a point source. So we might pair this point with that point, this point with that point, this point with that point, and so on. And so as long as we pair it with something that's equidistant from the center, they will constructively interfere. So now the question is what happens at increasing angles? Remember, angles means further up the screen. Theta measures the angle relative to the horizontal. So eventually, we will reach an angle so that each Huygens point, I'm writing this out because it's important, on one side of the center of the center line has a mate that has path length lambda over 2 longer. Notice, by the way, that I'm talking about lambda over 2 and not lambda, and that's because that's for a very particular reason. So the picture here is, how do I want to phrase this? So let me draw a picture again, and I'm just going to look at a few of these Huygens points. I'm going to draw it large, so obviously not to scale. So let's say that we have a point at the very top. Let's say that we just evenly split it, so that we're only looking at 4 points. There are more than 4 points. There's an infinite number, but we're only going to look at 4 because these 4 will let us describe what's happening here. So here's 4 equally spaced points. And so let's say that we're at this angle here. So there, Oh, I cannot draw a straight line. There, there, and there. Right, so they'll all produce light because they're Huygens points, so they all individually act like point sources, so they'll all produce light at that point, or sorry, send light to that point. So if we reach an angle such that, say, this point, oh, and here's the center line, by the way. Say this distance here, if we form this triangle, and we form this triangle, those two triangles would be identical. If this distance is lambda over 2, then this point, that's, you know, a third of the way up, as it were, or sorry, a third of the way from the bottom, will destructively interfere with the point on the bottom. But because of the symmetry here, the top point will also destructively interfere with the point 2/3 of the way down. And if you were to look at any point, they would precisely have one point that they destructively interfere with. That would be another point, another third or 2/3 of the way below it. So this distance here, sorry, this is a terrible drawing, because this distance is supposed to be a over 2. Let me redo these drawings. So we don't want to include points at the edge because they behave like half a Huygens point. So let's do 4 equally spaced points. I did not have to erase all that. That's a bummer. 4 equally spaced points with 2 around the center point, right? All right, now I can redraw this. So basically, the reason why my explanation didn't really, or why it's still, the explanation's still the same here, is that I didn't actually argue anything about the shape yet. Because all I'm saying is if this angle, sorry, if this path length, and now I have to zoom in to make it really small, if this path length is lambda over 2, and this path length is also lambda over 2, then we would get destructive interference between those points. And so the whole point is a dark fringe will occur when each point can destructively interfere with exactly one other point, or with at least one point. So the question is, where does this happen? Like at what angle? And so, by the way, this distance now is a over 2. And this distance is also a over 2, because they're halfway away from each other. So we need that lambda over 2 is equal to delta x, right? Delta x being the path length difference. So that means that we need the distance between the points to be, i.e. the distance between the points that are destructively interfering with each other. We need that distance to be a over 2 in this case. Sorry, the path length difference, which is lambda over 2, is just the distance between them times sine of the angle, as is tradition. So this is equal to a over 2, the distance between those points, times sine theta. And I'll give more explanation as to where this a over 2 came from, by the way. So how do I want to phrase this? So perhaps let's look at a different example, or the same example, but in a different case. Let's look at the point at the very top, assume it doesn't behave like half a Huygens point, and the point in the middle. Because if those two destructively interfere, then every set of points, you just shift, you just look, if you look at one point, you just look at the next point shifted halfway down. Obviously, those two can destructively interfere at some particular angle, because that would just be like a double slit. We couldn't choose any larger separation, though, because if you chose, say, a over 3, let's say you chose these 2 points to destructively interfere, then what does the point in the middle destructively interfere with? There's just nothing that's far away with. So it has to be a over 2 or smaller, because you need the middle point to be able to destructively interfere with something, and you need the top point to be able to destructively interfere with something. That's why A over 2 is chosen here, because that is the first place where you can have destructive interference, the first distance between paired Huygens points. The bottom line then is that the first dark fringe occurs when sine of theta is equal to plus or minus lambda over A. It's a fact, and it's because of this relatively messy explanation I gave. Let me give another example so that you can see so you can perhaps better understand why this is happening. So what if destructive interference occurs for not the mates across the central line, but between closer Huygens points. So what we looked at is we looked at the very largest separation that you could have for destructive interference to occur. Complete destructive interference, meaning that every point destructively interferes with another point. The reason, and so the smallest separation, the largest separation could be A over 2. So what if the separation between 2 points that are destructively interfering is smaller? What if it's like A over 3 or something? Well, let's look at another example. So I'm going to draw this large. So let's say we have a point up top. We have another point here, another point here, another point here. And so this distance is going to be, let's make this not equally spaced so that it's correct. So this distance, let's say, is A over 4. By the way, you might be able to justify why A over 3 might not work. Why isn't my, oh no. You might be able to justify why, yeah, no, sorry, it's just my notes got cut off at the bottom. See? So I have to infer. So basically we want to have, so the width here is A, right? So let's say that we just look at pairs that are A over 4 apart. And the reason, by the way, why we're going with even numbers is because if we went with odd numbers like A over 3, you'd end up not being able to pair them. They wouldn't pair up well. You have to be able to take 2 of those things, some multiple of 2 of those things, and get the total width. So if this distance is A over 4, and say this distance is A over 4, and then you'd have another point here that's another set of points that's another A over 4 distance. Basically, we're just going down A over 4 however many times. We would find that in order to get destructive interference, we would need lambda over 2 is equal to A over 4 times sine of theta, which would imply that sine of theta is equal to plus or minus 2 lambda over A. By the way, this whole plus or minus thing is because the whole thing is symmetric, right? So the angle could be positive, i.e. going up from the horizontal, or negative going down from the horizontal, but it's the same phenomenon. So that's why we're getting another slit here. But the point is we get a second dark fringe at the angle corresponding to sine of that angle being plus or minus 2 lambda over A. And the reason we call this the second dark fringe is because this occurs at a larger angle than the first dark fringe, right? If the sine of the angle is larger, then the angle is larger. And so if the sine of the angle, in this case, the sine of the angle is twice the sine of the original angle. So you could do this with A over 6 or A over 8, but try it with A over 3. I challenge you guys to try it with A over 3. You'll find that it just doesn't work out. Because pairs will start, or points will start having to be paired with more than one point, which is not particularly, it makes the problem not particularly simple. And indeed, you wouldn't find complete destructive interference there. So we can extrapolate this pattern, hopefully. And we find that the dark fringes occur when sine of theta is equal to plus or minus m lambda over a, where m is an integer. And indeed, you can go home and you could actually test this yourself, and you would find that this is what you measure. So it's the results agree, and I put to you to try to explain why a over 3 doesn't work for slit separation. I promise it doesn't work, but for the sake of time and for the sake of explanatory power, I'm not going to. So in this case, the bright fringes, the bright fringes are equally spaced between the dark fringes. So, and on top of that, the central maximum, perhaps you can understand why this is the case, is 2 times as wide as the double slit central maximum. Now, why is that the case? Let's go look up let's look at the distance between the central maximum and the first dark spot. So this is assuming that A and D are the same. So the first bright spot for the central maximum occurs at sine theta equals lambda over D, right? It's d sine theta equals lambda is the first bright spot. But the first dark spot for the single slit interference effect is sine of theta is lambda over A or lambda over D, depending on how you want to call it. So because the dark spot occurs where the first bright spot would be for the double slit, that means that the double slit's first dark spot has to be halfway between the central maximum and its bright spot. So there's a dark spot that is twice as close, or half the distance, to the central maximum for the double slit as there is for the single slit. Hence, you get that the central maximum for a single slit is twice as wide as the double slit, as the central maximum for the double slit. Which is, strange, but perhaps not. I mean, they're different phenomenon, so you shouldn't expect something different. Now we get into some of the worst formulas that we're going to see in this course. So let's look at the intensity. So as before, we're looking at the intensity at the single slit, by the way. Intensity depends on relative phase. Of source waves, depends on the relative phase of the source waves, right? So for a double slit, there's only 2 waves, right? The point is that you just have to add up, you just have to find the difference between the total phases of those 2 waves, and then you can just, the intensity just depends on that. It's like this, the cosine squared of that phase difference divided by 2. But for the single slit, ironically, there's way more slits. There's an infinite number of waves here. Like why, like how do you deal with the fact that you have to add up an infinite number of waves to figure out where the intensity is highest and where it's smallest? And so what we end up having to do is we have to do an integral rather than just adding up 2 cosines, we have to integrate a whole bunch of different cosines. Basically, it boils down to squaring the integral of cosine of x dx. So I don't actually want to go that far. But the point is for the double slit case, we have to we take the 2 waves, add them together, and that will give us the amplitude at various positions, or yeah, that'll give us an amplitude as a function of position, and then we square it to get the intensity, effectively, how the intensity relates to the maximum intensity. Here, we want to add up an infinite number of things. That is just an integral. And so what we're basically doing is we're adding up cosine of x plus phi 1 plus cosine of x plus phi 2 plus cosine of x plus phi 3, and so on and so forth. ad infinitum, and then you're integrating. Basically, from phi goes from 0 to 2 pi continuously. The end result, though, is actually fairly nice. The result from this type of calculus is that I of theta, this is the intensity as a function of position, sorry, as a function of angle, is equal to I naught, that is the intensity of the central maximum, times sine of alpha divided by alpha squared, where alpha is equal to pi a over lambda times sine of theta. So it's messy. This is definitely a messy formula. If you were to plug in alpha, it looks even worse. Again, this I naught is the central maximum intensity. I never promised that this formula, in fact, I tell every class that I lecture for 9B that these formulas are going to be the worst. The formula that you're seeing now and the formula I'm about to show you later are really bad. Alternatively, you could write this in terms of position. So this is position along the screen for small angles. This is I naught times sine alpha. This doesn't change over alpha squared, where alpha equals pi ay over lambda L for small theta. So this equation is equally good as long as it's small theta, because the approximation holds. And then you can check. You can check that the formula holds for dark fringes. If sine of theta equals lambda over a, this is the first dark spot. Or, by the way, the reason we call them fringes rather than spots is because they usually, if you're using a slit rather than a hole, they usually appear as lines, hence fringes. The first dark fringe from the formula above. That means that a over lambda times sine of theta is equal to 1. So alpha is equal to pi, and so I of arcsine of lambda over a, all I'm saying is plug in theta such that it solves this equation, equals I naught times sine of pi divided by pi squared, which sine of pi is just 0. So we get that we have 0 intensity at the dark spots that we were using before. So the intensity function is something called the sinc function, and it looks something like this. I will do my best to recreate it. So there's a central maximum. And so this gap here, this has a length of 2 lambda over a. And then each of these lengths would be lambda over a. And this is I. By the way, this, I'm not actually plotting a particular variable here. Really what I'm plotting is I'm plotting the sine of theta, if that makes sense. So this is like, this axis goes as the sine of theta, perhaps. Okay, great. So that's all of the single slit. Things get just a smidge more complicated. What happens? What happens now if you have finite width with double slits? So now we're combining the two phenomena. So no longer are your slits finite or infinitesimal in width for your double slit, and also now we have 2 single slits. You could view it either way. So we combine the effects. Yeah, so the horizontal axis is the lambda over a, that's just a distance, like along the horizontal axis. so sine theta, the distance between those 2 points is lambda over a. So that's just saying that sine of theta here is lambda over a smaller than the sine of theta here. That's all. Yeah, that's for the whole middle hump. That's this distance here. I was just telling you the distance between them. And so the point is that you can plot this thing. You can actually see that the central maximum is twice as large as the other maxima. Right. So what we're going to do is we're going to combine the effects from the single and double slits. So a question you might ask is, and by the way we're going to do this is just by combining the formulas. So what happens when one formula says we should get a bright spot, and the other formula says dark spot? So we're going to combine these two formulas, but we need to be able to understand what happens when one formula says that you should have a bright spot and the other formula says you should have a dark spot. Well, we know that the dark spot should win. Because the dark spot means that there is destructive interference happening at that point. And so regardless of whether or not that destructive interference is from the double slit effect, meaning that each of the two single slits, the wavelengths from one single slit are destructively interfering with the light from one single slit is destructively interfering with the light from the other single slit, that will produce a dark spot. Or even if an individual single slit would have produced a bright spot, they can still destructively interfere because there's still a path length difference between the two slits. Or alternatively, if the double slit would have said that we would have had a bright spot, but the single slit would say no, there's a dark spot there, that would mean that the light from a single slit is 0 at that angle. So how could you combine two zeros to get a bright spot from the double slit? So in fact, what happens is that the dark spot should win, which indicates that what we really want to do is we want to multiply the intensities, because 0 times I naught is still 0. So a dark spot should win over a bright spot, and so so rather than just adding up the intensities, for example, we see that we should multiply them. So let's just actually do it now. Oh, come on, scroll. There we go. For two slits of width A, separated by a distance d, we have the following setup. So this distance here should be A, this distance here is A, and then this distance, the distance between the center lines, that should be D. The intensity formula, so it does check out, because there are still bright spots, and those bright spots will be even brighter than what you may have expected. The intensity formula is this. So this is for small theta, small angles, because I'm going to use y. And now I write out this horrible, nasty thing. So I naught is still the brightest intensity you get. It's the intensity at the central maximum. Cosine squared of pi dy over lambda L times sine of pi ay over lambda L divided by pi ay over lambda L squared. That is the intensity formula for finite width double slits. What does it look like if we were to plot it against y? Looks something like this, and I'm going to do my best to make this look good. It's so hard to draw. Oh, where'd it go? The point is there's an envelope that looks like the single slit. And then there's also the individual brightenings and dimmings that occur from the double slit effect. So we're just combining the two effects. We're assuming that D is larger than A, but you know, you don't have to. You can plot this for various things. Just what I would suggest is just try plotting this for various values of A, lambda, and L. Like choose L as 1 meter, choose lambda as like 500 nanometers, and then just see what happens when you play around with A and D. But this is what it looks like. So I'm going to get rid of the envelope again. It looks like you have a very bright spot. This is I naught. And then you have a bunch of smaller bright spots close to it. But there is a place where even if there was a bright spot, you'd have a dark spot there. These would be the minimums from the single slit effect. And so you get this nice thing. And actually, when I was showing you what was happening with the hair, this is actually what I was showing you. And you couldn't see it, unfortunately, but this is actually what it looks like. So you get a whole bunch of very close together slits, very close together bumps, but you have the intensity dropping off with distance. So this is why this actually happens, and this is why it's impossible to produce a perfect double slit phenomenon, because your slits always have to have width, so the intensity will drop off as you get further and further away up the screen. All right, changing gears. So that's it for interference when it comes to multiple slits or slits at all. We're going to look at other types of interference now. Now we're going to look at interference. By the way, interference still always happens because there's phase differences, but there can be different sources. There are different ways of producing those phase differences. So the example that we've been talking about is you split the light, and then you have it interfere with itself in various ways. And that's a double slit, multi-slit, diffraction grating, single slit. It's all the same stuff. There are other ways that you can make light interfere. So another way that we can get light to interfere is from reflections. So typically, interference sources of light that interfere with each other, are separated side by side. Right, this is the picture of the double slit. And then you'd have some interference because they travel a different distance, you know, delta x, right? But you could have separate, so we still want to deal with interference coming from a path length difference, but we could have interference separated in a different direction. What if they were separated, the interference sources were separated along the direction of motion? What if you had two sources, one of which was in front of the other? Then how could you get those two to interfere? Well, it's kind of hard to do in practice, or you might think it's hard to do in practice, but it turns out that there is a relatively easy way to do this. Let's have light, the same light source, reflect off of two surfaces, one after the other. So the picture here, and I'm going to do my best to draw it, and I will explain why this is a bad picture. So you have your light wave coming in this way. It bounces off the first mirror, the first light wave, goes off this way. Or some of this light passes through, bounces off, and then goes through this way. Now, there's trouble with this drawing. I can't draw it so that they're overlapping, because then you won't be able to see what's happening. So instead, I draw it as if it were coming in at an angle, like so then you can see that they are coming from different places. But imagine that these were overlapping. So you just shine the light straight onto the mirror. Some of the light reflects off the first surface. Some of the light passes through and reflects off the back surface. Then the emitted light will reflect straight back up again, right? And so then you could have two waves that are in the same place and could interfere. So imagine that these are overlapping. In this case, the waves have traveled different distances, the reflected waves. Right, one only traveled this far. One of them traveled this far plus this far. So the distance that one traveled is smaller than the other. I mean, just because one of them went through, continued onto the back source, and then reflected. So how do you get this to happen? How do you produce these reflections that can also transmit? Well, oh boy. Here's something to recall from a while ago. It's really just 2 weeks ago. Waves reflect when the medium changes. But they also transmit. So remember back when we talked about waves on a string, and you had a thick string and a thin string? Well, all we were doing was changing the medium. That was changing the speed of wave propagation in the string, right? One of the strings got thick, so it had a smaller wave velocity. And so when you change medium and you change the wave speed, some of your wave is going to reflect when it is incident upon that interface. Some of the wave will continue through. So what we can do is we can just have 3 layers, all made of different stuff. So you will get reflection and transmission through each layer. So the way we do this is we use a thin film, like a thin layer, like think a thin film of grease, of a different medium. You actually don't need 3 media, you just need 2, really. Use a thin film of a different medium, so it reflects off the front and backside of the film. So imagine that we had like air here, and then we had like glass here, and then we had air on the other side. So because the medium is changing, there's 2 different interfaces. You'll have reflections from both of those sources, or sorry, from both of those interface changes, and then we can get interference between the reflected light from the 2 different interfaces. That's just an example, and we'll do more examples like this. So before we talk about this, we actually need to have a quick aside. We need to talk about what happens to light in a medium. We already know that the speed changes, because speed always changes in a medium, or usually changes in a medium. But we should be more specific. So what happens when light changes medium, or light enters a medium, say? Remember, it doesn't really need a medium, but it can travel through a medium. In that case, it changes speed, and that is medium dependent. Not so surprising. Remember, this is true for dependent, nope, I was writing too many words, too many letters. Just like on a string, the speed of light also changes depending on the medium. So for light, the change of the speed is controlled by a measured quantity called the Index of Refraction. You may have heard of this before. I can spell this. Index of Refraction. Not diffraction or diffraction. And this it's a number. This Index of Refraction is a number, and it's usually labeled by n, the letter n. So we would say the Index of Refraction of glass is 1.6-ish. Index of refraction of air is 1, and so on and so forth. So the fastest light can travel is the speed of light that you're all familiar with. It's 3 × 10⁸ meters per second. And this is in a vacuum. This is with no medium at all. this has n equals 1. A vacuum has index of refraction equal to 1. In a medium, the speed of light is c, the number c, 3 times 10 to the 8 meters per second, divided by the index of refraction. So if you know the index of refraction for a material, you can find the speed of light in that material by just dividing the speed of light, c, by its index of refraction. And just as a corollary of this statement, this means that n has to be greater than or equal to 1 for all media, because nothing can travel faster than the speed of light, so n always has to be greater than or equal to 1. So it gets a little bit complicated, right? Recall that v is always equal to lambda f. That's just definitionally true. If v changes, what happens to f and lambda for light? So remember that f is determined by the driver. Right, the thing that's causing the wave to propagate determines the frequency. For example, if you wave your hand on a string quickly, it'll produce a high frequency wave. If you wave it slowly, it'll produce a low frequency wave, and it produces a wave that is equal to the rate at which you, or the frequency at which you oscillate your hand. So it shouldn't depend on the medium. So f shouldn't change. The same is true for light, by the way. The frequency shouldn't depend on the medium. It's the wave speed that depends on the medium. But if the frequency stays the same and the wave speed changes, then that means that we should have that lambda, the wavelength, changes when the medium changes. So that's the thing that actually changes, the wavelength itself, not the wave frequency. So what we find is that the wavelength gets shorter when light goes from a vacuum to a medium, because the speed of light gets smaller. Speed of light gets smaller, and so lambda has to get smaller to compensate. So, so we can write this mathematically relatively easily. We know how the speed of light is related to the index of refraction, and so on and so forth. So for a medium 1, we have f lambda 1 equals v1, which is c over n1. That's for medium 1. For medium 2, we would have f lambda 2 is equal to v2, which is equal to c over n2, right? So so I'm just writing out a relationship between lambda and n, see lambda and n for different media, 1 and 2. So that tells us that n1 times lambda 1 is equal to n2 times lambda 2. That's the relationship between wavelength and index of refraction. So if you double the wavelength, then you have if you double the index of refraction, you have the wavelength, because you can always check it against a vacuum. All right, so now I have 6 minutes to go back to thin film interference. I will do my best, but we'll probably have to continue this on Wednesday. That was just a quick aside. So recall that the interference depends on the total phase. Total phase delta phi, which is 2 pi delta x over lambda plus, and remember we always absorb the delta t into the total change in phi phase, so we have plus delta phi there. So we have to consider both effects, in this case, for thin films. Why do we have to consider both effects? Well, okay, so the reason we have to consider both effects is because depending on how the medium changes, you either get an inverted wave or an upright wave, remember? That's what we've talked about with the wave on a string, and the same is true here. And that's equivalent to a phase change by pi. So that would mean that delta phi is pi when you have an inverted or upright wave, relatively speaking. I'll get to that in a little bit. But there's another subtlety here. The thickness of the film plays a role. So if the thickness is tau, Greek letter for t, then one wave travels 2 tau further than the other. That implies that delta x equals 2 tau. So the picture here is you have one wave coming in, you have this thickness here, which is tau. That wave reflects off of both. So this distance here is tau, this distance here is tau, because remember, they're supposed to be like straight on, so the angles are just there for visualization. So it travels 2 tau further, right? Also, the index of refraction plays a role. Because when we talk about how much further along in a cycle a wave travels, that depends on the wavelength, right? So not only is it the distance of the thickness of the film that the wave travels, we also need to take into account that the wavelength outside of the film is different from the wavelength inside of the film. The wavelength changes in the medium, i.e. 2 pi delta x over lambda. This lambda here refers to the wavelength in the medium, in the film. So put into words, the lambda in the delta phi refers to the wavelength while traversing the extra distance delta x. Because what we really care about is how many fractions of a wavelength has the wave traveled. And if the length itself has changed, then the amount of fractions of a wavelength will change, depending on what the wavelength is. The last feature is that there is a phase change from reflections. So here's one of my famous recall moments. When a wave reflects, let me try to draw this, see if I can draw this well. Well, there it is. When a wave reflects off a slower medium, i.e. it's going from fast to slow, the reflection is inverted. Inverting a wave is precisely the same as causing a phase difference of pi, right? If you flip the wave upside down, that's the same as just shifting the wave over by pi radians. So the picture here is, remember, you have a wave traveling towards, say, what is it? This is a slow medium here. On the inside the slow medium, you would have this ghost wave that is coming back towards, and it reflects and produces an inversion. So in the last 30 seconds, I will just do a very, very, very quick example. So those are the 3 factors that can occur, by the way. There's the distance covered, the change in the wavelength, and the phase inversion, or the reflection inversion. So let's talk about glass as a quick example. So the index of refraction of glass is about 4/3, and the index of refraction of air is about 1. So let's just use those values. So here's a picture. We have a thin film of glass, like maybe a window. We have a vacuum over here. Oh no, let's use air. We have air over here, and we have air over here. And you have light coming in. So delta x is equal to 2 times this distance, say d. And so, and delta phi is equal to pi. Now let's think about that for a minute. Why is delta phi equal to pi? Well, we know that the light speed is slower in glass, right, than in air, because it has a higher index of refraction. So the first interface, this interface here, this produces an inversion. I don't have room to write that. Inversion from this interface, because the light reflects off of an interface that's going from fast to slow. And when the light reflects off of this side, we have no inversion, because this is light reflecting off of an interface where the speed goes from slow to fast. You have an upright wave. I know I'm going over, just give me another minute or so. So that means that one of the waves is inverted relative to the other wave, which means that we get a phase difference of pi, because one wave is inverted relative to the other. So that's why we get that delta phi is pi and delta x is 2d. Now, the wavelength in the glass is equal to the wavelength in the air divided by 4/3 from this formula up top, if the index of refraction in air is 1. So this is that is to say that this is 3 times the wavelength in air over 4. So lambda phi is equal to 2 pi times 2d divided by 3 lambda in air over 4 plus pi, which can be simplified to 16 pi d over 3 lambda air plus pi. That's only true for this particular scenario, by the way. It's just true in this example. So for example, if the wavelength in the air and d conspire, like if it just happens to be the case that like the wavelength and the distances are precisely the values necessary to make delta phi equal to, say, pi or 3 pi or 5 pi or whatever, then we would get destructive interference, which means that none of the light there would be no reflected light, because all of the light is destructively interfering. And I'll talk about this in more detail on Wednesday, but the point is when that happens, you get 100% transmission through your material. Whereas typically, glass will typically reflect about 4% of your light. If you conspire to make your thickness of your glass and your wavelength, whatever, you'll get 100% transmission. Sorry, you'll get 96% transmission through typical glass. All right, sorry I ran a little bit over.